Good morning and welcome back to the MCAT grind. We have Biochem, Chapter 11, Lipid and Amino Acid Metabolism. We're getting near the end of the biochemistry, yay! But anyway, for transport in lipid and amino acid, this chapter is particularly low on the yield, probably like 2%. You're probably at most gonna see one discrete question, but no more than that. Now, but still, I want to learn this as much as I can just because I want to get the max score, right? Anyway, transport, we have triglycerols and they are turned into monoglycerols in the intestine. The way they can do that is being broken down by bile into smaller droplets and then eventually using the lipases secreted by the pancreas. When they've been converted to monoglycerol plus fatty acids, they will be packaged into chylomicrons and sent across into the lacteals and be sent through the lymphatic duct up towards and then join the bloodstream at the vena cava later afterwards, after it has passed through the liver already. So it will not go through the traditional intestinal route directly, unlike how glucose and other proteins, amino acids does. So fat-soluble, huge molecules like monoglycerol and fatty acids and the vitamin D, E, A, K, the fat-soluble ones, have to perspire through as chylomicrons. And then once they enter lacteal, then they can be turned back into triglycerols when they will go ahead and be transported in different forms. So we have the short-chain fatty acids, and short-chain fatty acids will go directly into the bloodstream. So only the larger chains, fatty acids, and the monoglycerols will need to go through the chylomicrons. The other vitamins, the water-soluble ones, like vitamin B and C, so on, they can go directly into the bloodstream. Lipid action come in many forms. The chylomicron itself is triglycerol, cholesterol, and they transport directly from intestine to the tissues. Now, what usually happens is that they will need to go to the liver first. So the triglycerol and fatty acid will go towards the liver, and from liver they will be delivered to tissue through the very low density lipoprotein. And if you want to go from the other way around, cholesterol from the high density lipoprotein and low density lipoprotein back to the liver is through intermediate density lipoprotein. So think about starting off, you want to get very low chylomicrons and then get bigger and bigger. As very low chylomicrons, you go to your liver, and once you're there, they come into more bigger bits as very low density, and they go and travel out, deliver to tissues, and then come back a little bit more bigger after collecting the cholesterols from there. Low density lipoproteins is basically the cholesterols directly going into the cells themselves. And the high density lipoproteins are the cholesterols that come back into the liver. So low and high density, they go back and forth. Low density lipoproteins are particularly not as good because having higher amount of cholesterol in the cells can induce bad conformations and diseases. So you want to remove the cholesterol from the liver from the cells using high density lipoproteins, so you don't have any as much clogging up your bloodstreams as you can. Intermediate density lipoproteins is particularly good as well because it brings the cholesterols in the blood into the liver. So what the density means that increase in protein to fat ratio. So the more dense it is, the more protein. Fat is not as dense. We have our two essential fatty acids, which is alpha-linoleic acid as well as linoleic acid. Humans can only produce palmitate, the fatty acid palmitate. Okay, so we need to derive the linoleic acid from the food we eat. And let me quickly check what food it is because I did not see an example. Linoleic acid foods. Yes, it's particularly in sunflower, soybean, corn, and canola oil. So pretty much if you use vegetable oil to cook, you'll get linoleic acid. We also have beta oxidation, fatty acid synthesis, this is probably the one question you're going to get regarding how fatty acid is transported in. Main thing is they need to attach to a CoA, just like acetyl-CoA. They need to attach to a CoA, and then they will need carnitine to shuttle them in. Once they've been shuttled into the cell, passed into the membrane, then they can undergo beta oxidation. Once they're in the mitochondria, they can undergo beta oxidation in these steps. Oxidation, so they lose an electron, then they hydrate with H2O. Basically, so after oxidation, they gain another bond to oxygen, right? So another double bond to oxygen, then H2O comes and split that bond and reduce it. Then oxidation again, turn into carbonyl, 2 into O. Then that's split again with CoA, so that splits into 2. What this does is that it derives the energy and forms it over and over again. So it takes apart the CoA in the process of forming the fatty acid itself. So when you have an odd number of chains, that can actually lead to generating a compound that's an intermediate of the Krebs cycle, succinyl-CoA, which comes after succinate. So this is the only time where fatty acid can actually enter the Krebs cycle, is through an odd number amount of fatty acid and undergoing beta oxidation, then entering acid cycle, the citric acid cycle, the Krebs cycle, through succinyl-CoA. Then we also have the ketone bodies, which is made from acetyl-CoA. They can generate acetoacetate and 3-HB. What ketone bodies are mostly used for is in prolonged fasting in the brain, where you will need to use it. Your brain starts to convert using ketone bodies up to 60% and 66% using ketone bodies as an energy source, and the other will still use glucose, primarily because the blood in your brain will need to remain on glucose to survive. But other parts, they can use ketone bodies. Alright, that's pretty much it.